Okay, now today what we're going to work on is section 2.1 in finite notes. So if you can get out those little finite note packets, and we will be working, I don't know what page it is, but section 2-1. We'll be talking about systems of linear equations. A system of linear equations is just a collection of two or more linear equations, each containing one or more variables. Now I have this little chart set up here that I have our system of equations, and I have it branching off, it's kind of, guess, like a tree diagram, into two separate sections. We either call them consistent, where we have at least one solution in common. Um, that means a ordered pair, or some ordered triple that works in all equations. Or we have what we call inconsistent systems, in which we have no solutions, basically. So this one is no solutions. And an example of this would be our parallel lines. Now, under consistent, we have two categories. We can either have one solution, or we can have infinitely many solutions. Infinite solutions, just write it like that. One solution, we say that we basically have an intersecting lines. And then we say that these are independent. Now let me kind of draw a line down the middle here. Infinite solutions are basically, if you have infinitely many solutions, what you're saying here is that you have the same line. Now remember, our new term for the same line is coincident. And these are going to be called dependent. These equations are dependent if they're infinitely many solutions, and independent if it's one solution. Okay, so that's just a new terminology of this section. And I'm going to be doing just some examples here with you. So example 1, I have 3x plus 2y equal to 2 and x minus 7y equal to negative 30. Now I know some people like substitution and some people like elimination, so I'll try and do both. I'll do this one using substitution because I can see right there that the x can be by itself very easily. X is equal to, add 7y to both sides, so I get 7y minus 30. So that means I go to the first equation. Wherever I see an x, I'm going to put parentheses. And in those parentheses, I'm going to put the 7y minus 30. So I get 21y. 7 times 30, that's going to be my 90, plus 2y equal to 2. So add the y's together, collect like terms, so I get 23y. And I'm going to add 90 to both sides, so that's going to be equal to 92. Divide by 23, so I get y to be 4. Plugging back up into my equation, remember my equation was x equal to 7y minus 30. I would get x equal to 7 times 4 minus 30. So 28 minus 30 is negative 2. So I have my ordered pair, negative 2, comma 4, x, y in alphabetical order. Since I have a solution, we would call these consistent, and they are independent. So just using all the terminology that we have there. If I go too fast, just be sure you can pause so you can get caught up. Just let somebody know, whoever is running that mouse over there. Example 2. 3x plus 2y is equal to 2. Oops, no it's not. How about 5? And then 5x minus y equal to 6. Now this one I'm going to use elimination just to kind of practice that one. We did these, I think, the other day in class with some of those story problems. I'm going to eliminate the y because I would just have to multiply this second equation by 2 in order for those y's to cancel. So what I would get, I always rewrite them, 3x plus 2y equal to 5, and 10x minus 2y equal to 12. So what I get here then is 13x equal to, oh wait, I did something wrong. I wrote the problem down wrong. I'm like, wait a minute, something's not right. Okay, let me see my mistakes. This is a negative. Always helps to write the problem down right. So I'd have to multiply everything by a -2. Okay, now I'm up to speed. Now you guys probably already caught that. I'm a little slow. Not paying attention here. So if I multiply through by -2, I could get a -2y and then a positive 2y. Okay, here we go. So then I would have here a -10x plus 2y equal to -12. That's working out. See, I didn't think I had any fractions coming up, and that's what threw me for a loop there. Okay, so 3x and -10x is -7x is equal to 5 and -12 is a -7. Therefore, x is 1. Plugging back into one of the originals, it doesn't matter which one. 3 times x, so I'm going to put a 1 there, minus a 2y, that was my mistake, is equal to 5. So I get a -2y. I'm going to subtract 3 from the other side, so I get a 5 minus 3. So I get -2y equal to 2, so y is going to be -1. Ordered pair, x is 1, y is -1. Now I call these consistent because we have a solution and they are independent. Okay. Now, the problems on the next page, I'm just going to maybe just kind of show you some, I don't know, some tricks, just kind of jog your memory on some of these special cases that we have and keep using the correct terminology. So example 3. I have x minus y equal to 5. I'll try and remember to copy the problem down right this time. X minus y is equal to 5 and -3x plus 3y is equal to 2. And I'm going to eliminate the x. So if I want to eliminate the x, I'm going to multiply the top equation by 3. So what I get is 3x minus 3y equal to 5. And my second equation, -3x plus 3y equal to 2. When I add these together, what happened is not only did I eliminate the x, but I eliminated the y. So now I got to look and see, do I have a true or a false statement? Well, everything canceled out on the left side. And on the right side, wow, I made another mistake. I'm going to have to listen. I'm going to have to pay attention here. Okay, 3 times 5 is 15, plus 2 is a 17. So I look at that, and that is a false statement. If it's a false statement, that means you have no solutions, and it is inconsistent. So these were two parallel lines. Okay, if it's a true statement, then you know it's the same line, and basically it's infinitely many solutions. And I'll show you how we're going to do that one. Okay, example 4. Here I have 3x minus y equal to 7 and 9x minus 3y equal to 21. So I'm going to eliminate the x again, and this time I'm going to have to multiply the top equation by -3. So I get a -9x plus 3y equal to -21. Second equation, 9x minus 3y equal to positive 21. Now, if I look at this one, both the x's and the y's canceled over here on the left side, so I get a 0, but so did the 21 and the -21. Now, it doesn't have to be 0 equal to 0. It could be like 5 equal to 5, depending on how you set up your equations. But the point is that it's a true statement. So the true statement means we're going to have infinitely many solutions. We call these coincident. We call these dependent. Now, how do I write the equation? We write the equation by looking up here. I can look at this equation, 3x minus y equal to 7. take that first equation. Can I very easily get x or y by itself? And that answer is yes, I can. 3x minus 7 is equal to y. I have infinitely many solutions. You cannot just say all real numbers. That's not an option. Okay? All real numbers just means you can pick out any two numbers you want and say that's a solution to the equation. And in fact, that's not necessarily true. So what we have to do is we have to say, okay, let's let x be anything we want. That's our all real numbers. Y depends on what we pick for x, and y is going to be my 3x minus 7. And where we can say where x is arbitrary, meaning you just pick x to be whatever you want it to be, but then y is going to have to be 3x minus 7. So that's how we deal with those type of problems, and that's how we write the solution. Okay? Example 5. Oh, that one looks fun. I see three variables, x, y, and z. So example 5. X minus y equals 6. 2x minus 3z equal to 16. 2y plus z equal to 4. Alrighty. I think what I'm going to do is I'm going to put these first two together. Let's put those two together first. X minus y equal to 6 and 2x minus 3z equal to 16. Now if I'm looking at those two, I'm going to eliminate the x because that's the only thing they have in common. So I'm going to multiply that by negative 2. And what I get here is negative 2x plus 2y equal to negative 12 and 2x minus 3z equal to 16. So when I add those two together, the x's cancel like what I had planned. Now the y's and z's you cannot add together because you have to have the same variable. So I just write 2y minus 3z equal to negative 12 plus 16 is 4. Now I'm going to look at my third equation that I haven't looked at yet. I have not addressed that one yet. Notice the equation I just finished up with has y's and z's in it. Go to that third equation, it has y's and z's. Now what I can do is put those two equations together. So I'm going to take, I'm circling them in black, this one, and put those two equations together. Okay, so here we go. I have 2y plus z equal to 4. That was one of my original equations. Here's my solution when I put the first two equations together and did elimination. I'm going to look at that, and I think I'm going to eliminate the y variable by multiplying that top equation by a negative. So this is what we get. I get a negative 2y minus z equal to negative 4. 2y minus 3z equal to 4. So when I add those two together, the y's cancel like I wanted them to. Two negatives, so I get a negative 4z equal to 0. So z in this case is 0 because negative 4 divided by 0 is 0. Now remember, when you add two negatives you are going to get a negative. Now I need to work backwards. Okay, let's look here. I had a 2y minus 3z equal to 4. If I plug a 0 in there, 2y minus 3 times 0, I'm going to get 2y equal to 4, therefore y is 2. Now I'm going to go back to an equation that has an x and a y in it. X minus y is 6. That was one of my original equations. Y I now know is 2, so I have x minus 2 is equal to 6, therefore x is 8. The way we write this in alphabetical order, just don't circle them. 8, 2, 0. That is what I box in. That is my solution to that system of equations. Okay, now this is where they start to get a little bit more complicated, so stick with me here. Example 6. 2x minus 3y minus z equal to 0. I'm going to put the first two equations together. But look at these. They all have x's, y's, and z. Now, I said I was going to put the first two equations together, and I'm going to eliminate a variable. Say I want to eliminate the z. If I do that, what I'll do then is take that and maybe put it with, maybe take the second and the third equation then and put those two together. And if I do that, I have to eliminate the same variable. So let's get started on that. If I take the 2x minus 3y minus z equals 0, match it up with negative x plus 2y plus z equal to 5, add those two together, I get x minus y equal to 5. The z's canceled. Okay, so since the third equation still has x, y, and z, I can either put the first and the third together or the second and the third. And I'm actually going to do the second and the third, because I see that the z's will cancel without me doing anything. So if I put those two together, I get 2x minus 2y equal to 6. Now whenever I see this, 2, 2, and 6, I think, well, they're all divisible by 2. So let's divide everything by 2. Just to make it easier, x minus y equal to 3. Okay, now we take and put those two equations together. So here's my x minus y equal 5. And here's my red equation, x minus y equal to 3. Well, you probably already saw that maybe that's not going to work. So if I multiply the top equation maybe times negative 1, what I get is negative x plus y equal to negative 5, and x minus y equal to 3. Add those two together, what do we get? 0 equal to negative 2. False statement. False statement. So what do? Inconsistent. No solution. Okay, bummer. Okay. Most likely, example 7, we're going to be able to get a solution, and I did leave you plenty of room to get that done. So stick with me here, only a couple more problems. Example 7. Let me write it down here real quick, give you time to get caught up. Okay, I'm going to put the first two equations together, so I'm going to write them over here. X minus 2y plus 3z equal to 7, and 2x plus y plus z equal to 4. And what do you want to eliminate? You want to eliminate the x? Does that sound good? So, can't hear you, so I guess the answer is yes. It's so boring with nobody here. Okay, so I'm going to eliminate the x by multiplying the top equation by negative 2. So what I get then is negative 2x plus 4y minus 6z equal to negative 14. Bottom equation stays the same. And the x's cancel. 5y minus 5z equal to negative 10. And let's take that down a little bit. Let's divide everything by 5. Y minus z equal to negative 2. Okay, next thing I'm going to do is put the second and the third equation together. So when I do that, 2x plus y plus z equal to 4, 3x plus 2y minus 2z equal to negative 10. It might have been easier to eliminate the z's to begin with. I'm seeing that now, but I've already eliminated the x's, so we're going to continue with that, and this is good review. I have to eliminate the x's in this system right here that I'm working with as well, since I did earlier. So I look at the 2x and the 3x, and I'm going to have to multiply top equations, or both equations, by a number. I'm going to multiply the top equation by negative 3, the bottom equation by 2, so therefore I'd get a negative 6x and a positive 6x, and those would cancel. So this is what I get. When I multiply that negative 3 times everything, I get a negative 6x minus 3y minus 3z equal to negative 12. When I multiply the 2 times everything, I get a 6x plus 4y minus 4z equal to negative 20. Add the two together, the x's cancel. So I get a 4y minus 7, I don't get 4y, I get a y minus 7z equal to negative 32. Okay, now I'm going to circle in black these two equations right here. Now I put those two equations together. So here they are. I'm going to write them down here in blue. Y minus z equal to negative 2, y minus 7z equal to negative 32. Let's eliminate the y. So I'm going to multiply this top equation by a negative. And what I get is negative y plus z equal to 2, y minus 7z equal to negative 32. Add the two together. So I get negative 6z equal to negative 30. Therefore, divide by negative 6. Z is equal to 5. That's one of my numbers. Now I know that y minus z was equal to negative 2 here, so I get y minus 5 equal to negative 2. Add 5 to both sides, so I get y to be 3. Now let's go to my original equation where I had x minus 2y plus 3z equal to 7. So I get x minus 2 times 3 plus 3 times 5 equal to 7. And I get x minus 6 plus 15 equal to 7. So I'm going to get x equal to 2. Is that right? How about negative 2? All right, I was doing my mental math and I was just forgetting my negative. There we go. Negative 2, 3, 5. Solution. Now I know those take a little bit of time. Don't get math ADD on me. Just be patient and you can get through those. Okay, example 8. Example 8, a movie theater charges $8 for adults, $4.50 for children, and $6 for senior citizens. One day the theater sold 405 tickets and collected $23.20 in receipts. There are twice as many children's tickets sold as adult tickets. How many adults, children, and senior citizens went to the theater that day? Now, we could go through that and write our equations and not have to do a chart, and that's okay. I'm okay with that if that's workable, doable for you. But I, the other day, introduced you to my chart system, and for those of you who like it, here it is. Let's do adults, let's do children, and let's do senior citizen. And then we have total. Okay, now when we did this, we always said we had an amount first. Here would be price. And then we had value. Okay. Now, reading through this again, it says the adult tickets were sold for $8, children for $4.50. I don't think I'm just going to put 4.5 instead of 4.50. And senior citizens are at 6. One day the theater sold 405 tickets, so that would be my total of my amount, 405 tickets. And I collected $23.20, so that would be my total value, $23.20. Okay? Now what I'm going to do is, when you do these problems, you really should somewhere write, let x equal to whatever, let y equal to whatever. Okay, so we'll see what we're going to do here. It says here that there are twice as many children's tickets sold as adults. So I'm going to let adults be x. So if there's twice as many children tickets as adult tickets, I'm going to let children be 2 times x? And we don't know about senior citizens, so we're going to let that one just be y. And I could say, we'll let 2x be equal to children's. We really wouldn't have to put that one, but we will. Okay? Now, filling out my chart then, I can go on and say I multiply amount times price, so I get 8x there. And then 2x times 4.5. Well, 4.5 times 2 is 9, so I know I'm going to have a 9x there. And then just a 6y. Now, where are my equations? Just like what we had before. Is this a highlighter? No, that's not. See if I can find my highlighter that I like to use. I don't know, that looks kind of dark. These two are my equations, these two rows. Okay? So here's my equations. I write x plus 2x plus y equal to 405. And I'm going to simplify that down to 3x plus y equal to 405. And then my other equation I would have would be 8x plus 9x plus 6y equal to 2320. Let's combine that to be 17x plus 6y equal to 2320. And again, here you can do substitution or you can do elimination. I like elimination, so I'm going to do it that way. 3x plus y equal to 405. 17x plus 6y equal to 2320. So I'm going to eliminate the y term by multiplying the top equation by negative 6. So what I get would be negative 18x minus 6y minus 20 equal negative 2430. And then I have 17x plus 6y equal to 2320. So when I add those two together, I get negative x equal to negative 110. So x is 110. And then I also have to solve for y. So I know that 3x plus y is equal to 405. Y is going to be 405 minus 3x minus 3 times 110. So I get y to be 330.75. So here's what we have. X is equal to 110 adult tickets. 2x would be 220 children. And y is equal to 75, which are the senior citizens. And that is how we do those story problems. Okay, so again, the chart is optional, but I think it helps. Alrighty? Okay, the sub has the rest of the stuff for you to do today. But hopefully we have an understanding of how we solve systems of equations in section 2.1. Thank you and have a great day.